Good morning, students. I decided that I would record the lesson you can listen to today with the school closure and then take a few notes and do a few practice questions. When we're back in the lab next Thursday, we will then look at a few of the practical bits associated with this lesson. So we're just going to finish off our topic, electromagnetic induction, chapter 28 today. So recalling, first of all, what electromagnetic induction is, meaning that whenever the magnetic field passing through a coil changes, an EMF will appear in the coil. And this is the phenomenon we call electromagnetic induction. Today we're going to look at two other concepts associated with that called mutual induction and self-induction as well. So if we think of the word mutual in everyday language, it would be between two things or between two people, for example. So in terms of electricity and induction, when we talk about mutual induction, it's going to be again between two things. And this experiment we actually saw at the very start of the topic when we started this chapter. So to define mutual induction, it means if a changing electric current in one coil causes an induced EMF to appear in a nearby coil, there is said to be mutual inductance between the two coils. So you can either pause the presentation here and note this, or you can at the end go back to the parts where you need to note the definitions. The experiment is the exact same one as you had at the start of the chapter when we were demonstrating electromagnetic induction. So I'm not going to get you to take a note of it again, but I will just talk through it here briefly. So we have the two circuits with coils next to each other. If circuit A is connected to a DC source and there's a switch on it, and circuit B is alongside it and we've connected that coil to a galvanometer, we can measure if there is a current flowing in circuit B if the galvanometer deflects. So what happens here is when the switch is opened or closed, very briefly there, the current will change and the magnetic field around it will change in coil 1. And then this changing magnetic field is passed through to coil 2. Your galvanometer will deflect, and that shows mutual inductance between the two coils, or passing from one to the other. You might ask then, how can the amount of mutual induction between two coils be increased? So think about that for a second. If we want to see a greater deflection there in that galvanometer, what could we change? There's three things we can change. So distance between them. If we move the coils nearer to each other, we would feel a greater force there, and there would be a greater amount of mutual induction. If they are wound on the same soft iron core, so we're going to see this concept a little bit in a minute, where the two coils on two separate circuits are related to each other by having a soft iron core shared in the middle of them. And a third one then would be the number of turns. So increasing the number of turns on either or both of the coils. And these concepts are what happens in devices called transformers and in a device called the induction coil. We're going to be looking at these as well today. So again, either pause the presentation here and take a note of the three reasons that would cause the amount of mutual induction between the two coils to be increased, or take a note of each of the parts at the end. Then we have a concept called self-induction, and there's a lot here now to the definition here for self-induction to take in. So whenever the current passing through a coil changes, we know that the magnetic field surrounding that coil changes. This changing magnetic field induces an EMF in the coil, and we know from Lenz's law that it opposes the direction of that change producing it. So it opposes that increasing current. So the changing magnetic field induces an EMF in the coil and opposes the changing current. And this EMF we call, it's a new special term called back EMF. Back EMF. And this is what we call self-induction. So the back EMF is like a pushback or an opposition resisting against it. If we wanted to demonstrate self-induction, we could connect a circuit like this, where we have a DC source, a switch, a bulb, all connected in a loop, and in that loop we have the coils of wire, and through the middle of it we can put a soft iron core. So what happens here is when the switch is closed, the bulb won't light immediately. There's a delay, and it would take a few seconds before the bulb would reach full brightness. So what's happening here is you have this build-up of the back EMF opposing, and this is what we call self-inductance of the coil. What happens in the circuit from closing the switch to this delay? It happens in, I suppose, a few small phases. Firstly, when we close the switch, your current will start to flow. When current starts to flow through a wire, we know it will start to produce a magnetic field around that wire. So there's a magnetic field building up around that coil, it's increasing, and the coil has a changing magnetic field while it's building up. So we know from Faraday's law that an EMF is induced in the coil. By Lenz's law, we know the direction of the EMF opposes the change producing it. So it's opposing the increasing current. And this induced EMF opposes but doesn't necessarily succeed in preventing the current from increasing. So this is called a back EMF. The result here is that it delays the buildup of current. This is the phenomenon we call self-induction. If you think of back EMF as pushback or opposition. So when you're taking notes from this slide here, it's just taking the parts in white, the first and second lines, and then at the end of the slide take down the term back EMF as well. Next to back EMF, write a note for pushback or opposition. So we can look at the effect of an inductor on AC, and we have here two very similar circuits. We have a 12-volt DC source connected to a 6 ohm resistor, and Ohm's law, your very important rule, you can work out the current flowing there through the wire would be 2 amps. If we change that source then to an AC source, what's happening is that the current flowing would actually be much less than 2 amps. So what's happening here, your alternating current is changing direction every 100th of a second, back and forth, and then the magnetic field around the coil would also be changing continuously. So bringing the two laws together, Faraday's and Lenz's law, an EMF is induced in the coil, and it's always opposing the changing current. So this will create a back EMF, and it causes the coil there to offer more opposition. So we'd have more opposition to AC than DC here in that second circuit. And the symbol there for an inductor will be nu. So if you see in the bottom circuit there, your 6 ohms, that's above the inductor, you literally will draw a coil of wire and a line underneath it. And that line underneath it, or that bar, represents a soft iron core, as if that iron core is sitting through the middle of all of those coils of wire. But we don't actually draw it through the middle of the coils, we draw the bar underneath the coils. So have a look in your log tables as well and be familiar where that electrical symbol is if you were drawing a circuit for an inductor. So if we look at a lamp connected in series with an AC power supply and a coil, and we try to explain why the lamp goes out when a soft iron core is inserted into the coil. So circuit 1 there versus circuit 2. So what's happening? The core there is moving into the coil, and it'll cause an increased magnetic flux in the coil, and hence a greater rate of change of magnetic flux. The coil then carrying that AC will have a back EMF, and the greater rate of change of magnetic flux will cause the back EMF to increase. So this actually pushes back against it and reduces the net voltage, and the current will decrease. So the lamp will go out because the current will actually decrease. And this is used every day in your homes in a dimmer switch. When you're actually turning the dimmer switch on your wall, what you're doing is you're moving a soft iron core in or out of a coil of wire, and you're changing this back EMF. So if you're applying a strong back EMF, that can be enough to, in some cases, totally dim or put out the light or change it to a dimmer value. And you do need to know an everyday use of a inductor. So if you were asked in an exam question to give a use of an inductor, the answer would be dimmer switches. So, so when we look at alternating current and inductors connected to AC sources, we can compare DC versus AC and what happens in each case. So a coil or an inductor opposes the flow of direct current only with its ohmic resistance. It won't succeed in preventing the flow of current, whereas a coil or an inductor opposes the flow of alternating current with two things, with its ohmic resistance and the back EMF induced in it. And it can succeed in slowing down current or preventing the flow of current in some cases. So that back EMF there can have a significant impact. So all of this needs to be noted in your notes, and if you were asked for a difference between an inductor connected to DC versus an inductor connected to AC, you would have to know that the AC opposes the flow with both ohmic resistance and the back EMF induced in it. And there is just the diagrams again showing the concept of the dimmer switch. So in that right hand circuit, if we moved that soft iron core back out of that coil again, the bulb would start to light up again because that back EMF would be reduced as the soft iron core would be moved out. Alright, so if you would like to pause the presentation and give a couple of questions there on page 324 a go, I'd like you to look at question 1 and question 2, please. Alright, so both of these questions are going to be relating to this concept of this back EMF. So I'll throw up the solutions there and talk through them. Question 1 asked us a filament lamp and a coil with an iron core are connected in series with an AC power supply of variable frequency and fixed voltage. If the frequency is increased, what happens to the brightness of the lamp and why does this happen? So similar to the concept there of the dimmer switch, for example, the brightness of the lamp would decrease because a higher frequency would mean a greater back EMF or a greater opposition. Question 2 then, a coil of wire of resistance 10 ohms has a DC voltage of 20 volts across its end. What steady DC current flows in the coil? And then if the DC source is removed and replaced with a 20 volt AC source, what changes, if any, would take place in the current and why? So first part of the question there, because we're working with DC values, we can use Ohm's law, current being voltage over resistance, and we see a current of 2 amps. Then we change that DC source to an AC source, and what happens to the current? The current will decrease because of the back EMF there again. Alright, so all down to that concept of the back EMF. There's a small section there on page 325 to do with capacitors and AC. We've had this before in a previous chapter when we were looking at capacitance. So if we have a direct current circuit connected to a capacitor and we have a alternating source connected to a capacitor, what happens here? So when the capacitor is fully charged there in the left hand circuit, no further current will flow. So it actually stops and it blocks your direct current. Whereas on the right hand circuit, because it's alternating back and forth, changing direction every 100th of a second, it is continually charging and discharging. So your capacitor there allows AC to flow. So we talk with this that a capacitor conducts alternating current and blocks direct current. I'm not going to get you to note this because you've had it before already. The final section now in this chapter is to do with transformers, and we're going to look at what we call a primary coil versus a secondary coil wound around a common core, and then comparing input voltages to output voltages. So if we think of the word transform in everyday language, it means to change. If you think of transformer toys when you were a kid, you had a man that changed into a car, or a car that changed back into a man, or whatever. So they were transforming or changing. Here we're talking about electrical transformers. So we're going to look at how they work. So a transformer basically is a device that is used to change the value of an alternating voltage. It can make it higher or it can make it lower, depending on the needs. So in your own time, again, please note and learn the definition here for your transformer. If we look at the structure of a transformer, then the picture on the right here is a soft laminated iron core. It's a square or a rectangular shape, and on either side of it there's coils of wire wrapped around it. So we call the left hand side there the primary side, we call the right hand side the secondary side. And we can count the number of turns on either side. So we can count the number of turns of primary, count the number of turns on the secondary, and we can apply an input voltage, and then we can measure an output voltage on the secondary side. So it will cause a different voltage then, because there are a different number of turns on either side to appear on the secondary side of the circuit. When we're in the lab on Thursday again, we'll set some of these up and do some measurements and prove the ratios. So what happens, excuse me, here on the left hand side is the input voltage, which we'll call VI, causes an alternating current in that primary coil, and this then causes an alternating magnetic flux in the iron core. So that passes right through that core over to the secondary coil, which then induces an EMF, which we call the output voltage VO, in that right hand side of the coil. And the size of this output voltage will depend on the number of turns in the secondary and the primary coils. So this, I need you to note in your notes as well, is the formula. We can take the input voltage VI divided by the output voltage and equate that to the number of turns in the primary over the number of turns in the secondary coil. And if we know 3 out of the 4 values, we can work out the missing value. There's 2 different types of transformer. We can cause an increase in voltage, called a step up transformer. So if the number of turns in the secondary is greater than in the primary, then it steps up. Whereas if the number of turns in the secondary is less than in the primary, then it will cause the voltage to step down. And we need both types of transformers to do different jobs. You'll have to note this slide in your notes as well, please. An application of step up and step down transformers is in our everyday electricity, how it gets from the power station to our homes. So in a power station, typically it will generate electricity between 20 and 30 kilovolts, and that is fed through a step up transformer to increase it to about 220 to 400 kilovolts for distribution over the national grid. It's put across the transmission cables, so the high voltage will mean low current, so there'll be less heat loss or dissipation during transmission through the power lines. Then, before coming into our homes, it needs to go through a step down transformer to decrease it to the 230 volts that we need coming into our homes and our houses. So this is what we will build in the lab now on Thursday. We'll build a circuit where we will have a number of primary turns wound around a soft iron core, a number of secondary turns on the other side, and we'll connect an AC source. So we'll connect a certain number of volts on the AC source. We'll stick a voltmeter in to measure it as well. And then on the secondary side, we will stick another voltmeter on. And we'll measure each of the 4 values and work out the ratios. and we're going to do this for a few different transformers. So we have all different number of turns in our lab, and we'll try a few of them. It's a very nice experiment to try. Alright folks, so that is reaching the end really of our chapter. There is a sample problem using that formula at the end of page 326. So have a look there at that sample problem 13 and practice it there with a few of the questions for your homework. So page 327, I'd like you to try questions 1, 3, 4 and 5 please. And hopefully you're all safe in the storm on Friday, and I'll see you on Monday. Thanks.